Yeah, so thank you, Nadia. It's really nice for me to give a talk here with this audience. And yeah, so I'm gonna follow, or this is like the next talk about multi-index stochastic collocation. So last week we have heard about this method with the talk of Joachim. And so today I'm gonna go ahead and compare and give a comparison of MISC, so multi-index stochastic collocation, and another method, so based on radial basis functions. And I'm gonna talk about a naval engineering problem. So we'll talk about UQ analysis of ship resistance. And yeah, so I'm from this Institute of, so IMATI, Institute of Applied Mathematics and Information Technology, Lorenzo Tamellini as well. And I want to mention also and to thank also my colleagues at the Institute of Marine Engineering in Rome, so Riccardo Pellegrini, Riccardo Broglia, Andrea Serrani, Matteo Diaz, that we work together on this project. Yeah, so you might already guess, so the people from the Institute of Marine Engineering, they brought this interesting application, so this type of ship, and then we together we carry out this comparison on these two methods. So I just want to give you a few ideas at the beginning, just some background. And I mean, we are talking about this ship problems, this naval engineering problem. And what one should take into account is that the ship performance depends on several parameters, so operational, environmental parameters, design parameters. So we can think at speed, the sea state, the payload, and many others. And the thing is that these parameters are affected by uncertainty. So they are highly uncertain, and therefore we need to do some forward UQ analysis. And I mean, the problem itself, it's a complex problem. So we have, I mean, Navier-Stokes equations, and of course we have also our ship, our vessel, no? So with 6 degrees of freedom. So we have this coupled problem, let's say, and I mean, solving these type of problems is a really realistic problem. This is very expensive. So there is the need for multi-fidelity methods, multi-fidelity UQ methods, and I mean, of course, you all know, so why do we use multi-fidelity methods? And the thing is that they explore the bulk of variability over inexpensive models, and they resort to the expensive ones, so to high fidelity models only sparingly. So, I mean, then we really take a couple of, so we take these two multi-fidelity methods, so MISC, multi-index stochastic collocation, and multi-fidelity stochastic radial basis function. And we perform this UQ analysis for a specific type of ship. So the Europax ferry sailing in calm water. And the two uncertain parameters are these two operational parameters, which are the speed and the payload. So, I mean, first thing, what is a Europax ferry? I mean, I didn't know about this before, so I didn't know that it was called, this kind of ferry was called like that. And I mean, this, so Europax ferry is a passenger's ferry, but I mean, this ferry can carry also cars, trucks, whatever. And so cars, they get into the ferry on their own wheels. So you do not need a crane to load them. So they get on their own wheels. So this is a type of ferry we consider. And the quantity of interest, what we are interested in is the resistance to advancement of this ferry. We consider it in straight ahead advancement. And as I said, we have two uncertain parameters, so the speeds, and I said the payload. I mean, instead of considering the payload, we actually work in terms of draft. We assume that they are uniform random variables. and then of course we have to give certain ranges for them. And I mean, here in the table, I just listed these three interesting metrics, let's say. So first thing, to have an idea about the size of this ferry, and to have an idea, we take these parameters, so this characteristic length, so the length between perpendicular. So it's LPP, which is depicted here. So when we take, basically, we look at a section of the hull of the ferry. And so at the full scale, this would be 162.85 meters, and then the speed range would vary between 12 and 26 knots. The draft would vary between 6.4 and 7.8 meters. But actually, okay, we do not work at the full scale, we work at the model scale. So, I mean, model scale is really the model the colleagues at the Institute of Marine Engineering are working with. And so these are like the rescaled length and the rescaled ranges for the two parameters. So this is basically just to have an idea what is our object. So what is the thing we are working with. And yeah, as I said, I mean, we have to solve Navier-Stokes. So the underlying problem has to be, of course, treated with Navier-Stokes equations, and the solver we are considering is a solver called Kinavis. It's an unsteady run solver. They have again developed at the Institute of Marine Engineering, and this is multi-block solver. So the domain we are considering is divided in blocks. These blocks are overlapping. The grids are also overlapping, and is based on finite volume scheme. What is interesting, let's say, to mention is that this is a multi-grid solver. And that's really important because then the multi-grid solver gives us all the grids we want to use as fidelities. So actually we are working with 4 grids, so with 4 fidelities. And these are like, so we have an illustration here. So this is basically we have the mesh, plot of the mesh around the bulb, and from the finest to the coarsest grid, so from left to right. And the thing is that each grid, so the next grid, is obtained by a de-refinement where we have a factor of 2 in every direction. So basically we glue together, so we combine together 8 elements here, and then we go there, and then 8 elements again. So there is a factor of 8, which scales going from one grid to the next de-refined grid. And I mean, then we take also this cost, so the scaling factor, 8 is also the scaling factor of the cost. So we normalize the first cost to 1, and then from the coarsest to the finest, we jump to cost equal to 512. So this, then we know how we get the different fidelities, and we can really now start to have a look at the 2 methods we compare. And the first thing I want just to say is like that we, so with alpha, we always, so in this talk, we will always refer to the fidelity in space. So alpha, we really take the value 1, 2, 3, 4 for the 4 fidelities. And I've said also we have 2 random parameters, and we collect them in a random vector, and we assume uniform distribution for them. As quantity of interest, we are looking at the resistance of the ferry to the advancement. And with G of alpha, then I want to denote the quantity of interest computed over the mesh specified by alpha. And I mean, then the ideal goal it would be like to have an approximation of the expectation of the quantity of interest over a very refined mesh, and using a lot of samples in parameter space. No? So this would be like just what I've written in the formula. So G of alpha star, where with alpha star we like indicate the very fine grid in space, and with J large means that we are taking a lot of samples. We are sampling a lot the parameter space. I mean, then the two methods, I mean, they just, I want to give you the main ideas of what is the difference between the two of them, let's say. And what multi-index stochastic collocation does is to replace this E of G of alpha star, so this very refined approximation in physical space and parameter space, with a linear combination of many coarser quadratures, so coarser in physical space and in parameter space. Whereas stochastic radial basis function, they would just like use standard quadrature. So for example, Monte Carlo quadrature on this formula here. But then instead of evaluating the full model, so evaluating the full G on the grid alpha star, they would replace the full model with a surrogate models. And then sample really these, evaluate these surrogate models. So these are the two things I'm gonna explain in the next. And so we will start with multi-index stochastic collocation. So I'm like, I don't know, we have heard about that last week, but maybe not all of us, all of you were there. So maybe it helps when I say a few words again. And then let's start. So as I said, the main idea of multi-index stochastic collocation is that we want to combine, to do this, to make this linear combination of coarser quadratures. No? And then I want just again to consider this Q of alpha beta. So this is the quadrature formula where we use this fidelity indicated by alpha, and then the number of sampling points in parameter space is given somehow by beta. In this case here, alpha, so beta has two components. Now we have the two parameters, so the speed and the draft. So we have a multi-index, so with three components. So we assume that, so I said at the beginning, so that we have a uniform distribution of this parameter. And so then we use Clenshaft-Cortis points. And the thing is that these are not random. So we can generate this sequence of points. And actually, how do we generate these points, or how many of them do we take? The thing is that we use this index beta, and the index beta should tell us how many points we sample. And the rule we decide to follow is this one. So basically, when beta is equal to 0, we take one sampling point. When beta is equal to 1, we take one sampling point. And then starting from 2, we follow the rule 2 to the power of beta I minus 1 plus 1. So this means that when beta is equal to 2, beta I is equal to 2, we would sample 3, then we would sample 5 points, and so on. So we get a sequence of Clenshaft-Cortis points, and the point is that this sequence is nested. And this is really like, I mean, this is a smart choice to do, because we will consider adaptive algorithms. So somehow the beta, so when beta is increasing, then all the points we use at the for beta smaller will be reused again. So we can recycle some computations, let's say. And so then we have basically, we can compute the points in one direction, so corresponding to the index beta 1. We have the points corresponding to the index beta 2, and then the grid, the sampling grid, we would have is then the Cartesian product of this univariate set of points. So this would be just what happens corresponding to one multi-index alpha, beta 1, beta 2. And then how do we go on? No? So how do we actually make this combination? How do we combine quadrature with different indexes? And the idea is really this what we call, or what is called sparsification principle. So now I mean, for the illustration, I just stick to the case when we have a one-dimensional parameter space. And so we have these 4 dots here, which correspond to these different quadratures. So the red dot would correspond to a coarse discretization. So when we would use a low fidelity model, and we would sample it on few points. Instead, when we consider the green dot, we consider a higher fidelity model. So we refine the mesh in space, but we still sample on few points. The blue dot instead has a higher number of samples, but these samples are, so we sample the low fidelity model. Okay. And the black would be our ideal, no? So the ideal discretization, which corresponds to many samples and a high fidelity. I mean, this would be too expensive. So how do we do? So how can we approximate this F by perhaps taking consideration these other coarser discretizations? So we can, just to understand the principle, we can write a telescopic equality. So we basically add and subtract these C, Q, and P here. And then if we rearrange them, we get an interesting thing. So, I mean, we could combine 1P with the minus C, Q with 1 minus C, then we would, we have 1 C left alone, and then F, a P, a Q, and a C. So when we look at P minus C, we see that basically here what we are doing, so when we compare the two of them, is just we keep the same fidelity, but we increase, so from C to P, we increase the number of samples. So this is somehow a correction in parameter space. Instead, when we go from C to Q, we are just increasing the fidelity. So we are increasing the accuracy in physical space. So this is a correction in the accuracy, in the PD solver accuracy. And then here F minus P minus Q plus C is somehow a mixed thing. So it's a mixed correction. And then so we hopefully, so we neglect the mixed correction. So of course we lose a bit in accuracy, but hopefully this mixed correction is small. And I mean, neglecting this mixed correction allows us to neglect actually the expensive thing to compute, no? So we lose a bit of accuracy, but we gain in computational efficiency. And then, I mean, we look at what is left, and okay, 2 C disappear, and so we are left with P, Q, and C. So actually, the sparser components or the sparser approximation. Okay, and then, I mean, we really can approximate F as P plus Q minus C. So this is a linear combination of 3 cheaper approximation, no? Because each of them requires fixing a mesh and the samples in parameter space, okay? And the point is that either I refine the mesh or I refine the sampling, or I have a finer sampling. Good. So this is the whole idea. And I mean, just to go back to our notation, so with the quadrature formulas, and getting back to our multi-index alpha beta, we have really that the discretization where we have the index alpha star and beta star is written as the combination with the indexes alpha bar and beta bar, which are the less refined ones, and alpha star beta bar or alpha bar beta star. Quite obvious, no? And I mean, this is then this is a linear combination, and somehow this like reminds what is happening in sparse, what is called combination technique in the sparse grid set. Great. So I mean, just now to put all the ingredients together, and I mean, at the beginning I said that So we are using clash of Cortis points. We follow a precise rule such that we have a sequence of points. Then we do this tensor product of the univariate set of points. We get Cartesian grids. And then when we combine these different coarse approximation, we get many grids. We have basically a union of grids. They are all structured, but they are not tensor grids. I mean, we get immediately a MISC quadrature formula. So that's how I explain the whole thing. So the sampling points are quadrature points. So we select them. So we get the MISC quadrature formula. And I mean, we should not forget that the underlying is, so there is a surrogate model. So, and this surrogate model consists of Lagrangian interpolants. So for each fidelity, we have somehow Lagrangian interpolants over the parameter space. I mentioned this sparsification principle. So the whole idea that in order to approximate this E of G of alpha star, we consider coarser approximation. And this coarser approximation actually, I mean, again, referring to the indexes alpha and beta, so what we want to have is to include approximation where alpha is small. So we have coarse meshes, but large beta. So we solve many PDEs on coarse meshes and just consider few solution over refined meshes, so with large alpha and beta small, so few solution over the refined mesh. And as I said, I mean, all these solutions are completely dependent. So we can solve in parallel, all of them, because we have all these scenarios that can be solved in parallel. And so scenarios, I mean, we fix the discretization in space and then we have the corresponding sampling. So we solve all of them and this can be done in parallel and the code can be completely, fully reused. No? So then, I mean, and the smart choice we have to make is how to select this multi-index set lambda. So how do we choose which multi-index is alpha beta? So how do we choose which discretization enter in the approximation? I mean, the spirit must be always the same so that whenever we refine in physical space, we do not refine in parameter space and vice versa. And or whenever we refine one parameter direction, we do not refine the second parameter direction and so on. So, I mean, this can be, how to do that can be designed a priori. So, I mean, this can be done studying the equation you have at hand and yeah, this has been done in the literature, or you can proceed in an adaptive manner. And this is the strategy we follow here. And we follow the Gersten-Gribel adaptive algorithm. So the idea is works like that. So, I mean, of course, we must start the first index, multi-index, again, we take is the multi-index alpha, alpha equal to 1 and beta equal to 1. Okay, so this would mean that I would take the lowest fidelity with one sampling point. What would I do next? I would look at the two neighbors, neighboring refinements. So I would refine a bit this, go to the next fidelity level with still one sampling point, or stick to the first fidelity and refine the space. I mean, the question is that which of the two is more convenient, in which direction should I proceed? And the choice is based on the best improvement. So which one of the two gives the best improvement? And the improvement can be measured in several ways. So, I mean, what we choose here is to go in the direction which basically gives the best improvement in terms of the expected value. So that's what is written here, delta expected value. So, and of course, this must be weighted by the cost. So, and the cost is here a product of two things. So the cost related to the fidelity. So the powers of 8 I've mentioned in the beginning. So 1/8 going to 512 multiplied by the number of new simulation I have to do, okay? And I mean, here comes the point of having the recycling of the grid points, because what I have here can be reused there. So actually in the cost of adding these, I have to add only the new simulation required, and a lot can be recycled. So then could be that turns out that this is the best. This is the index which gives the best improvement. And then what do? I take this and I move, I look again at the neighbor. Then between the two green, which one is the one giving the best improvement? Maybe it's this one this time. What do I look next? I look at all the neighbors, so all the green, and so on. So I mean, I would go on until I reach, I meet some stopping criteria. So it could be that I've the computational budget, the accuracy, some threshold, whatever. And okay, so that's the idea. And of course, choosing the best improvement based on the expected value. On the expected value is not the only choice. So this is problem dependent. Might be that it could be more efficient to look at I don't know, higher order moments, some other error measures, whatever. So this must be somehow tried out and checked. Great. So we now can look at stochastic radial basis function, and so we change perspective, change method, and I mean, I want to start just with the single fidelity approximation, just to understand what is going on. And I mean, SRBF, stochastic radial basis function. So so each fidelity is based on radial basis function with power kernel here. So the kernel parameter is this tau here, and this is stochastic, so it's random. So from this comes the word, so that we have the stochastic in front of radial basis functions. Then, I mean, the prediction of the surrogate model at each fidelity is a Monte Carlo average of different powers of tau. So we have different tau e, we average the results, and then we get the G tilde, which is our one single fidelity prediction, let's say. And then associated with each prediction, we have a certain uncertainty, which has to do with the variance of the parameter tau. So this is so we can look at this figure here on the right. And so for the moment, let's assume that the RBF centers, so these CJ, are equal to the training points. So these are the centers of the RBF are located at the orange squares here. And so then we have the RBF centers. We take into account a certain number of RBFs. We sample the kernel parameters. We average with Monte Carlo, and then we get our prediction G tilde. Yes, then what I've just explained is one possibility. So how do we choose the RBF centers? So we can either choose them to be exactly at the training point, or we can do something else. So let's say that for a fixed number of centers, capital K, we can follow two approaches. Either the coefficient Wj are computed by least squares or by interpolation. So the interpolation is of course, it's what follows if we choose the centers to be exactly the training points. Then the corresponding coefficients are computed by exact interpolation. Instead, we use least squares. So we compute the coefficient by least squares. And when the number of centers is smaller than the training set size. So in that case, the location of the centers is computed by a k-means algorithm, and the corresponding weights coefficients are computed by least squares. What's the optimal number the optimal number for k for the centers is computed by leave one out cross validation. And why do we distinguish between these two approaches? I mean, we introduced it has been introduced, the second approach with the least square regression, because it seems to be to perform quite well when we have training sets affected by noise. And this is what we observe, or what is illustrated here in the second figure, basically. Yes, so we then can construct the multi-fidelity model, and this is built by telescopic sums. So, I mean, here we have just an illustration with two fidelities. So we can, so the orange one is the lowest fidelity, so of the level 1. And then we basically correct the first approximation, so the orange one, by a surrogate model constructed on the error between the next approximation. So between the model I have attended and the training set. So basically, so the orange is corrected with the green to get the blue approximation. Basically, that's what it's written here, and this is just a telescopic sum. Yes, and then I mean, I've said, so we have seen clearly that from the plots that basically we always have a prediction answer. So each prediction has an associated uncertainty. And so this is what actually looking at the prediction is what we look at in order to drive the adaptivity process, let's say. So we add a new training point at the place where the uncertainty is maximized. Okay, so in the region with the largest uncertainty, we add a new training point. So somehow then it's clear that the sampling is deterministic, so it depends on the uncertainty, but it's completely unstructured. Then the training points are not quadrature points, hence we need the quadrature rule in order to approximate the expected value of our quantity of interest. And okay, for example, one could do a Monte Carlo sampling of the multi-fidelity surrogate model. Okay, so now I want to just tell you two things about the implementation of the SRBF method, just because these two information are useful to understand then the numerical results. I will show you in a minute. And so the first thing to mention is that somehow this adaptive method has to start somehow. So it starts considering 5 points per fidelity level. So that's what the choice we made. So the initial training sets consist of five points per fidelity level. And the next thing I should mention is that the switch between the exact interpolation and the least square regression for computing the coefficients in the SRBF is done when the size of the training set is greater than 25. So if we have less than 25 points, we use exact interpolation. When the training set is greater, the training set size is greater than 25, we go for the least square regression. Great. So then looking at the numerical results, I want just first of all give you the two plots of the sampling performed by the two methods, because I mean, that's what I've been like telling several times until now. So MISC works over structured grids, instead SRBF proceeds by an unstructured sampling. So this is actually really the superposition of Cartesian grid I've mentioned, and this is the sampling performed, and this sampling is just driven by the uncertainty in the prediction. So we are ready now to look at the convergence behavior of the two methods. And so we look at the expected value, and below we have the standard deviation, but let's just focus on the top plot, where we have that the blue curve is the convergence result. So these are the results for MISC. And the red dot is for the results of the SRBF. So we can first of all observe that, I mean, both of them kind of converge towards like similar estimates. So about 52 and 53, let's say, of expected value of the resistance. And I mean, MISC actually converges quite fast towards a good estimate. So around computational cost 900, we already reach a good value, let's say, a good estimate. And then, I mean, somehow what it seems is that this behavior, so the convergence behavior worsens a bit, let's say. And this happens around, I mean, here in this region, we are about the iteration 14. So I just, so just keep in mind this number 14. We need in the next step. Instead, when we look at the red curve at the results for SRBF, we see that, I mean, there is a quite high computational cost at the very beginning. And so this is due to the fact that the initial training set consists of these 5 points per fidelity level. So we have an initial computational cost quite large. And then, I mean, we can focus on this region here where you see this cluster of points. So, I mean, the convergence is oscillatory a little bit, let's say. And I mean, this behavior happens after the switch between the exact interpolation setting and the least square setting I've mentioned before. And so this is happening at iteration 8. So at iteration 8, the lowest fidelity changes strategies, let's say. And after that, so somehow what we can conclude here is that due to this clustering of points, it's that after this iteration 8, mostly low fidelities are included, no? So cheap computation are included. We can then really look in details at the sampling performed by the two methods. So let's say before and after iteration 14 for MISC and before and after iteration 8 for SRBF. And I mean, we observe that MISC somehow at the beginning explores more this direction, so the speed direction. So like somehow it seems that the parameter U has more impact on the overall approximation. Let's say that's what we can conclude looking at this plot. But then, I mean, when the iteration go, so when we proceed with the adaptive scheme, we see that like all the direction are kind of, or at least explored well, and a lot of points are added. Actually, I should mention that the different colors denote the different simulation on the different fidelity levels. So the blue dots are parameters which are sampled referring to the lowest fidelity. So on the grid M1, we sample the blue point. On the so the red dots are the points which are sampled on the grid 1 and grid 2, the yellow on the grid 1, 2, 3, and the crosses for these points are sampled for all the 4 fidelities. And I mean, so we see here that there is a lot of blue. So there is a lot of samples on the lowest fidelity. So this clearly gives some computational gain, but we should also mention that this computational gain is due to the fact that we have this anisotropy in the sampling. So we do not refine both the parameters simultaneously. When we look at SRBF, so here when we perform, so at the beginning we have this exact interpolation, and we see that somehow there is some clustering of points. So the points start to cluster in some regions. So for example here. And when we switch to least square, so these somehow then seems to prevent the clusterization of the samples. So the samples then turned out to be quite spread all over the domain, let's say. So, I mean, then following the same color, so like in the same setting, so we can again observe how the two methods perform, how do they perform the sampling, no? And I mean, here we have the number of iteration required, the number of simulation required per grid at each iteration, no? So we go from iteration 1 to iteration 30. And we see that, I mean, when we get to the end, so the last iteration, we consider we required about 200, 180 simulations on the courses grid. And then some on the on level 2 or 3, and on the finest grid, we require just 5 simulations. And these 5 simulations, so the first one maybe you do not see, is asked at iteration 5. So here we ask for an iteration. So MISC asked for one simulation on the finest grid, and then 2 more are added quite later. So quite late at iteration 24, 28, and iteration 30. Instead, when we look at the SRBF, I mean, again, so we see that, okay, also here, many samples, but maybe just 45 samples are asked on the courses grid. And actually, in total, 9 simulations on the finest grid are required. I mean, the point is that 5 are already at the beginning, so just to start the process. So 5 simulations on the finest grid. And then at iteration 5 and 6, we have 2 more, so 4 in total. So we have in total 9 simulations on the finest grid versus the 5 asked by MISC. And yeah, I mean, as I mentioned, so this training set we need at the beginning is quite expensive. So already 50% of the final computational cost is used at the first iteration. Then when we look at the results, so on the top, so the first 2 plots on the top are about MISC, and the second row about SRBF. We observe that basically the result of MISC at iteration 14 is quite, like, let's say, reasonable. But I mean, this behavior then worsens a bit. That's what we already expected looking at the convergence plot. So the surface is very irregular, and this has to do with the numerical noise in the data we have. So especially the courses grid produces quite noisy simulation. So then this is the result. Actually, SRBF instead it gives quite better results, let's say. But when we look at the beginning, so the result at iteration 8, where we are enforcing the interpolation, we see that there is this little bump here. So somehow this has again to do with the noise. So if you remember, this was the region where we had this kind of clustering of sampling points. I mean, this what here, no? This region where we had some starting of clustering of points, let's say. And so then this is also reflected in what we get for the response surface. And somehow then the least squares seem to like smooth out this. So they are quite effective in filtering out the noise. I mean, MISC clearly not. And this has to do with the fact that the surrogate model, the MISC is a Lagrangian interpolant, so combination of Lagrangian interpolants. So that's it. I mean, then when we look at the PDF, we then can say nothing else than again confirm the same thing, no? So the good news is that both methods predict a same peak, so around 30 newtons, so really a similar peak around 30 newtons. But then when we look at the at MISC, we observe this spurious, this second peak here, no? And this again is nothing else than what we have already seen in the plot of the response surfaces. So that's basically the comparison with the two methods, between the two methods, and I I'm basically at the end. I just want to summarize what we have seen, what I've told you till now. So, I mean, we have looked at the convergence plot. We looked at the response surfaces, PDF. So we can conclude that both methods, so MISC and SRBF, are both viable alternatives. So for realistic problems, so they give they give reasonable results. Let's say very similar results. And what else can we say? So we could say that MISC could be preferred when only limited computational budget is available. So in the convergence plot, we have seen that until this iteration 14, at iteration 14, we already got very good approximation of the expected value. So when the computational budget is limited, maybe one could choose multi-index stochastic collocation. But then, I mean, if larger budget, so it's available, maybe one should choose SRBF. And the reason is the robustness to noise. So we have seen that this introducing the least square regression, the SRBF gives a robust approach with respect to the noise. And so somehow then it's also kind of clear what we want to investigate in the future, let's say. And I mean, for MISC, it would be really interesting to find a strategy to mitigate the impact of numerical noise. So like we need some smoothing of the results of the solver. And the big, a problem with SRBF is really the initial computational cost, which is quite too large, let's say. So again, if we would find a strategy to reduce this would be really interesting to do. And of course, also considering more complex cases, so like including more parameters, more realistic random variables and conditions, this is also something we would like to investigate in the future. So I'm really at the end now, and I just want to give you 3 references. So the first one is available in the archive. So it's the paper where we really explain in details. You can find all the details of what I've told you today. And then I have 2 references, one for MISC and another one for SRBF. So thank you a lot.